Ya, Hugo, tú nos dices, nos das el...
Adelante, adelante, ya.
Bueno, ya voy a anunciar. Bueno, gracias por su asistencia. La siguiente plática dentro del seminario de Lyapunov va a ser dado por nuestro estudiante de doctorado, Hasan Raza Mirza. El título de su plática, Oscillations, Oscillation of Current Carrying String in a Magnetic Field Bifurcation Time Series and Phase Portrait Analysis of the Driving Mathieu-Duffing Oscillator. Well, the idea of this Lyapunov seminary consists is allowing that the student, postgraduate student, can show the advance of the research. I prefer that at the end the question, or do you prefer during the presentation? Okay, no. As you want. It depends. It depends on the topic. Yes. I think it would be better because it's the seminar, so we will ask questions during the presentation. It will be easier to follow. Okay. Well, Hasan, please, can you start your presentation?
First of all, I would like to thanks to Dr. Hugo and Dr. Guillermo and Dr. Leaders for giving me this opportunity. And lastly, I highly grateful to Professor Dr. Avajani for throughout his talk. So let's start with our topic. So my topic name is Oscillation of a Current Carrying String in a Magnetic Field. We study the bifurcation time series phase portrait analysis of a Mathieu-Duffing driving oscillators. So here is the content. Here is the content which I will elaborate during my discussions. So give introduction, I'll present my mathematical model, we do some discussion on my results. After that, conclude my work and what we will do in futures and the present references I will list in the slides. Moving forward to the introductions, as you are seeing here, we study the transfer nonlinear oscillation of a current carrying string in a non-uniform magnetic field. But to study this system, we use some key approaches like Lorentz force, it obtained using the interaction of the electrical current with the magnetic field, thermally induced parametric excitations, and geometrical nonlinearity, which came with the tension variations. With these assumptions and approaches, we obtain the coupled nonlinear integral differential equations. Since it is in a complicated form, we want to reduce them to more simpler form to study and analyze in more better way. So we use a single mode approximations, and with that single mode approximation, we obtain the driven Mathieu-Duffing oscillators, which is our objective of our study. And on this system, we do further analysis. So moving forward to our mathematical model. To drive our mathematical model, we transfer oscillations of a current carrying string under the alternate electrical current and non-uniform magnetic fields. So as you are seeing in the reference number 1, he used the strategy of a, because the slides in PDF, so you destroy the original structures. So in the reference number 1, he studied the thin rod and he used the approximation of like study then transfers, oscillations, longitudinal and the torsional effects. But we assume the thin string and we, with some assumptions, we reduce the torsional effect and still we have a longitudinal and transverse effect. and we use this reference number 3, which is a professor's book, in which he elaborated the Lorentz force, which is acting as an external force. So he elaborated different cases. So we use one of them cases to state our system. So with that, we obtain the, and still we have a system in a longitudinal and transverse one. So we use the assumption of a planar motion. With that assumptions, we can separate the longitudinal and the transverse one. And we use Fourier expansion in normal nodes, and we obtain the equation number 1, which is still look in a complicated form. So we want to reduce them. So to reduce this system, we use a single mode approximation.
Can you explain, please, what is the difficulties for the complexity of the equation? A little bit more details about the equation 1. Equation 1, what each term express.
Okay. So here, like a first term is an acceleration term. You know, this is a damping terms. This is a damping term, and beta is a damping coefficient. And here, this is term is obtained by the Joule heatings, and this is a terms obtained by the geometrical nonlinearity, and this is the external driving force. So right now it is a general form IFT and FN, and it is a Fourier special component, and IFT is a Lorentz force. Still, it is in a complicated form, so we want to reduce them.
But why? Why it's complicated?
Because the Lorentz force is in a general form. So it's in
There is a term with the sum. It's you see that there is a coupling here.
coupling value.
This is the most important, but not most important, one of the important things that complicate the resolution, because it's coupled the different modes of the transversal oscillations. Even the longitudinal oscillation were separated from the transversal one. You have the coupling between the transversal modes through this term, this last term before the equal.
This couples with the stiffness. Okay. So we want to reduce this equation number 1. So we use a single mode approximations and harmonic electrical current for our initial study.
Can you explain, please, what is the single mode approximation? And what does it mean here? Equation 1.
With the single mode approximation, we use here we convert this system into a like a single form. It is like X M, and in M, so we use that single mode and we reduce them into this form.
Okay. In other words, the physical limit of this reduction is that the sum is for all the modes, the sum over n. You reduce it to this sum only one selected mode, which is you suppose, like in this example, the most important, maybe for some reason, but it could be any one of n, because you have equation for any modes, but any nth mode is related with the others one. So when you choose one mode as preferential, or for some reason, physical reason, mathematical reason, and so on, and you say that the other modes are not so important, so you reduce the sum only one. For example, you want to study nth mode, and somehow by physical reason or some other one, it's selected or preferable or dominating mode. So all the sum over n, you reduce only m equal in n. So that's why you can. It means what is single mode approximation, which is given by the second equation.
Okay, see the equation number 1 and number 3. The sum term relationship with the mode. Yes. La término de sumatoria corresponde a los modos. Bueno, aquí. Si consideramos dos términos de la sumatoria, en la ecuación 2 tendríamos dos términos, un término adicional.
Okay.
O
Voy a
in-
explicar en español, o en inglés. Okay. You can choose, let's say that the
Two-
two modes are
two mo-
important.
yeah.
Two modes are important. So you have to write two equations. And each equation, each mode is coupled with the other one. You will have two oscillators coupled. And so you can, from the equation one, you can couple potentially any number of selected modes and consider it's what will be its glance in a little bit. It will be about next law, which sure, but to see the coupling.
And this is a hypothesis or only, or there is a physical reason to take only one mode approximation?
There is a physical reason. It's superposition. Usually made in all previous works or in most of the previous works. But they, for example, when you excite, as in this apparatus, the first spatial mode, you know that the other does not influence much. So you suppress all others and you study only the first one, mode, the spatial mode and the temporal component of this. But it's not excluded that under some conditions that it's so expected for the non-uniform magnetic field, we can couple effectively two or even more modes, and so the spatial vibration will be quite different. Not only this, quite a mix, but stable mix. So this is there are some physical reasons to do this kind of mathematical.
Okay, the physical, but if I will try to see the equation 2, the first term is linear stiffness. Let me
Stiffness?
stiffness.
Stiffness.
Linear stiffness. The second is non-linear. Yes.
Yes.
But if we consider the another mode in the equation, maybe we have some plus, some constant, and t upper 4 or upper 5. You don't try to.
No, we didn't try the higher order coupling. It could be done, but you see that the coupling is for Tm is square, Tn is linear for the given n.
Yeah.
But
Sorry.
when you multiply, Robert, make a product.
Do the product.
The product, so you have the third order term or nonlinearity. In single mode approximation, it's a little bit more clear because it's exactly Tn to the third order, and so this is a cubic nonlinearity of Duffing.
Yeah. Because Duffing can be has or Duffing can has more components. For example, here the nonlinear components is T upper 3.
Yes.
It's possible you have in Duffing plus constant T upper 4 or constant T upper 5, depends how you decide. And this the term linear stiffness and nonlinear stiffness depend is this parameter. It can be double well potential, doble pose de potencial or tres pose de potencial. If the multi-stability or B-stability depend how we can build or depend on this parameter, we have double or three, as this give idea the stability or multi-stability. Be stable or multi-stable. This depends of the components nonlinear. When you draw, you can.
Okay. It's one of the possibilities. We do not explore this yet, and the physical part indicates us to limit us for this approximation, because we use also the pre-expansion for the inside of the integrals, and so it gave us this term in brackets, in top brackets. If we do not use, if we use higher order approximation, probably other terms will also
Have some effects.
appear. But for us, it's quite important to follow the physical meaning of this equation, not to invent and to add something else. As Hasan showed, there are multi-stability here, even in this system. So it's quite enough for the moment. Please.
So this is equation number 2, and it is our objective of our study. So we do further analysis like its results and through the illustration of the bifurcation time series and phase coefficient. Shall we go next?
I suggest you also for other participants to once again everybody would give the explanation of the tools or the contributions, and which is Mathieu, which is Duffing, which is and so on and so on. What is the
Here the Duffing part is like this cubic and the external forces, which is related to the Duffing, and the Mathieu part is this one. So these are the
more should be, you should look. It's very important to give the knowledge what to explain the reason, mathematical reason, not only physical but mathematical reason for the effects you will explain. You have the second order. It's okay. It's common term for the oscillators. Second order. You have
In Spanish,
movimiento, damping, to be damping, and the term which is here is represents the constant part. It's a kind of omega square.
yes,
Angular frequency, but you have also the term which depends cosine term. This is typical for the Mathieu equation, typical. But also there is a very interesting relation between the frequency of modulation of the frequency. It's double omega, but the frequency of driving force is omega. They are not independent. They are dependent. They are dependent one other. It's interesting thing. Also, you have the constant term in the parentheses inside of brackets, CT square and so on and so on. It could be negative. It's first depending on the parameters. What does it mean? You can also how it will. It's not typical for the Mathieu. but it's physical reasoning. Okay. And there are quite fine details and very important. So when you impose this kind of, you have to fix to put the attention on for the details, give the importance of the equation. Mathematically, structurally, it looks like Mathieu-Duffing driving oscillator, but there are very important details here. Yes. If you do it something, no. Okay.
To do our numerical simulations, as you know, we have a second order system, the Mathieu-Duffing driven oscillators. So we want to convert them in a more simpler form. So we convert them into two first order ordinary differential equations to treat them in a more better way. So we convert equation number 2 into these two first order ordinary differential equations, and we use these equations to obtain our further results. Moving forward. I try to resolve it analytically, but I will use for example, I use a harmonic balancing method, but they have many suppositions and they neglect many higher terms, and with that we can't get the exact results. So that is why we avoid that technique and we come toward the numerical techniques. That's the reason.
Okay. One comment, please. We tried to have the balance, frequency balance method, but I analyzed it and it has methodological.
Tiene muchas restricciones.
Incongruencia metodológica. Nadie escribe esto, pero sí lo tiene, porque intentamos con 3 modos, con 3 frecuencias, etcétera. Está funcionando somehow. Para algunas cosas, etcétera. Pero de mi punto de vista está incongruente, así tiene, por eso lo descartamos. Hay métodos de perturbación que no son muy locales. Es que tú tienes este punto y alrededor de este punto tú ves que
Fixed point. For you try to find Lyapunov, very small in the neighborhood.
Yes.
Not general.
So we decided to work numerically to see the global dynamics of the system. Because we didn't find these results for the global, because continue.
Okay. So we came into this system, the equation number 2, this is a Mathieu-Duffing driven oscillators. Using this, and we obtain the following results. So first of all, this is the bifurcation diagram, which is obtained from the equation number 2, which is a Mathieu-Duffing driven oscillators, and we selected the range of the string temperature from 0 to 40, with the step size is 0.05.
Please. You have also to mention what is the temperature mean. The temperature here, or you mentioned this, it's the heating of the string over the environment temperature. You have a string at the environment temperature, but when the current comes through the heat is higher than the current. So the temperature here is delta T0. It's over the heating over this temperature of the environment. It's not inverted.
The idea is the temperature has a periodic behavior.
it has we have included this effect in the equation because there is the heating, even you have the alternating current. It's due to the thermic effects and dissipation of the color heat. You stabilize. You have some stabilized temperature. It's not follows the variation of the current. Because of the quite frequently it's inertial effect of the heat. But there is also a small oscillation over this basic temperature, over this incremental temperature. That is included in the terms of frequency modulation. And this is also very important. Let's imagine the temperature. Strain. It's under the tension. You heat it a little bit by the current, it loses the tension, but you heat it more, it can even lose completely the heat, and then you will. You have no oscillations. We have oscillation, but it's like without tension because you have the force anyway.
Okay, Lorentz force.
So it's interesting thing how. And there is a critical temperature of critical when the omega becomes 0.
So we selected the range of the temperatures, stream temperature. It is in between from 0 to 40, and on the vertical axis we use the initial conditions range in between minus 0.03 to 0.03. It's very small range with the step size 0.0012, very tiny small. So we see we want to see the more effects. That's why we selected very small time step size. So also the driving frequency, which is equal to 192.767 radian per second. This is the driving frequency which is equal to the natural frequency. So
natural frequency of the oscillator.
Natural frequency of the oscillators.
It's resonance frequency of resonance frequency, which not there are some tiny differences. Natural frequency does not include the effect of damping. But the resonance frequency includes damping. We have little damping for this example, so it's those who are quite close. So you can go with like natural frequency, but natural frequency without driving or without heating. No, it's really corresponds to the constant part of the frequency term.
Do you have a measure or some approximation about the natural frequency? Do you have which is the values of the
Calculated. It's calculated, not measured. It's calculated.
yeah, okay. Do you have some values? Because you apply the, for example, you use this omega. Why do you choose this value for a study?
But that's I try to explain that it should be done.
Yeah, why we choose this value? Because this is the value where the system driving frequency equal to the natural frequency.
Okay. Okay.
Resonance.
And you even have to put the expression of what is in terms of parameters to see. The omega is this and this. To be more clear for
the
Okay,
organs.
you choose this value of omega when in resonance frequency. Okay, because maybe in the future, or maybe in this presentation, you can show what happens when the external frequency is a little more large or a little less. Yes.
In next, we will explain. And amplitude of the driving force is 0.1. So with this, as you see it here, initially when the system starting oscillate, it have a depth of oscillation. With some passage of time, it is have a two-state solutions. When it reach here, it shows three-state oscillations, and when it reach to the critical temperatures, after that system is going toward the splitting the branches, and it is reaching toward the multistable.
The horizontal line, for example, between 0 up to 20, yeah, the horizontal line. It refers a fixed point, or what does it refer to this one?
This one?
Yes.
This one is a
Constant response or
No,
oscillation?
it's fixed, it's the depth of
Fixed
depth of oscillation.
Depth of
This line is depth of oscillation. This could be like
Coexist with some oscillate behavior.
oscillate.
By step.
Yeah, bistable I will show in a time series characteristics.
In the range between 2 degrees and 15 or something like this, you have depth of oscillations to states. But depth of oscillations, it depends on the initial conditions or oscillations on frequency of the. It's also a really interesting thing. We will show the frequency response of the system. There is oscillations. The branch is up to the 0. This one, it's oscillate. Those are oscillations. But frequency.
So, as you are seeing here, as the temperature increases, the system reaches from a simple to the multistable dynamics. And the general structure of this system is like a pitchfork-like bifurcation diagram. And from, if you see from here 0 to 2, system have a depth of oscillation, no further. From this 2 to 17, system shows two-state solutions, and from 17 to 90, it's very tiny range, where it shows three-state solution. This three-state solution, and after again it have a two-state solutions. Then when from here onward 22 to 30, it show multi-stability, and with increase of the more temperature range, it show a dense multi-stability in this system.
In the next class of the Seminario dynamic system, we will talk about the picture bifurcation.
One comment. We know what it's here. It's this bifurcation diagram is constructed using the technique of local max of the final oscillations. But I propose to use local max and and local minimum. I will explain the reason. And there is a difference between these two presentations because it's quite traditional when you have quite a bit of oscillation.
But okay, follow me.
Sinusoidal oscillations, there is no difference. It's the same information.
Yes.
But there are situations when they display different effects if you use both. We will see later a little. It's first. Second, if you pay attention, we see a kind of pitchfork after the critical temperature pitchfork. But there is branching in each branch, which is suppose that there is like how is it called? It's
Period.
Spanish.
not even in Spanish. It's bifurcation. Bifurcation. Yes, there are bifurcation and bifurcation, but the topological figures one.
Fractal.
Fractal. Fractal.
No, fractal numerical, but the system has two frequencies. Yes, natural frequency, external frequency. Maybe this like to points this part. If we try to analyze, or maybe it's you can try to see that it is a fractal, but maybe with a little careful, maybe you can find a sun-like torus.
Could be.
Could be in this number of points here. Maybe we can find torus because we have two frequencies.
Could be. Could be. Now I also put attention to your attention that there is a structure which similar but not exactly the fractals remind me.
We need to, it's necessary to measure that we try to prove that it is the fractal.
Locally, you have first pitch focal. Then you go to one of these branches, and you have other one. We didn't take, and so on and so on and so on. It's a kind of, I don't say.
Autosimilitude, we need to prove. If you measure autosimilitude in this picture, it's okay.
It's not our goal back the moment. We only pay attention to this. There is a kind of fractal structure in this bifurcation diagrams, and it's even more evident when we use local max and local min technique for the construction of the bifurcation diagram. Which
don't give more information when we try to analyze the bifurcation.
But when we are, I overlap, same time series, I overlap, have some confusion in next slides. I will show you and you can debate. And one thing is more like in my protocol, you are, I guess, Professor Gia, the professor, he asked a question about if we increase the temperature, what will happen? So I study further, like from 40 to 70, still have same like that branches. So it doesn't show any chaos in this system. So we study further.
swamps a bit different.
All the multistability or denser multistability. So these are the bifurcation, same time series, using the local mean.
Symmetry.
Symmetry.
Now, here you use the local mean. Don't give more information because it's a symmetry, because when you got time series that you find local, you find the mean.
It's a common. Okay.
Come here. Come to this.
Local max, local min.
These are the overlaps.
The picture is beautiful, right? But in by dynamic system, don't give more information.
It gives more information. There is a small detail which, at least for this system, in the windows which separated, you see the branching of the principal branch of the can you indicate it with pointer? Okay. If it was exactly the same information and so on, you have it only one line, but you have doubling here. You have splitting.
But here, what happened? Maybe if you do the same process, but you increase the control parameter delta T0 for large, what happened with the branch?
We don't know yet. We don't know yet, but we found it was Following your suggestions, we use the max, local max construction, and then it occurred to me to try to locally, and it apparently it's very connected. But when we overlap that,
No, you complete.
we overlap, when we overlap a constructed exactly, we found a split, and this is the physical explanation for this effect. With the high temperature, you have higher amplitudes because you local max and local min for the low temperature, it's almost the same because the amplitude of oscillations is very low. When you, at least in this scale, when you increase the temperature, they separate. And what does it mean? You have se ablanda el material, entonces con la misma fuerza tú tienes mayor amplitud. Y esta lo explica. Me dice, entonces, yo tengo unos ejemplos, pero después lo vamos a ver cuando sí puede ser la importancia hasta más crítica de aquí. De uso de local max and local min technique for extraction of bifurcation diagrams.
But as I saw many articles in all of them, approximately they use the local max technique. No person is concentrated on the local max because they more consider like a sinusoidals and also consider the last part. So they thought that the local max and mean give us same meaning. So
It's possible by successively Kirchhoff bifurcation when you plot local and minimal points, increase the parameter, maybe you will have successively Kirchhoff bifurcation.
We can suppose, let's say, there are two things. Mathematically, we can increase it up to the infinity, almost, okay, or significantly. Let's say 0, 100. Physically, it means that you have a unstable system because, as I explained it, when you have dilatation of the material, you have the string is it has no tension, the initial tension, and it's only here tension when it's in the extreme position. Let's say the force is put it here, and the tension it's returning force then. So we have to put it for mathematically, and then to see if it could be explained in physically. Yeah. Mathematically, it's quite good exercises to see, as you guess or suggest, what will happen. How we touch. Look. Also, even here in the range of 25, 40, you see branches very dense, it's line, continuous line, and you see also the structure which is not over this one, and let's say inside, and you will see that it gives like a multi-stable section, but it's dispersed. This one. This one. This is
The advanced setting we got for following.
So now, as you see in the bifurcation diagrams, it shows the states, and I want to illustrate and give justification through the examples. So I come to, I selected, fix it the temperature. It is 17.5 degrees Celsius. And I selected the time series sequentially from the range of minus 0.03 to the same step size. And these are the three sequential, 17, 18, and 19. As you see, with that tiny change in the initially it is a death of oscillations. With a tiny change in the initial condition, system goes to the resonance state. Again, with the tiny change, system obtains the death of
So the
oscillations.
depth of oscillations.
Similarly like that.
Which value, 0 or which in the last part time is 0 or which value has? No, here.
Here,
No, next.
this one,
Yeah, this
which is at 18.
but in the attractor involved up
Yeah,
to
this
which
is
value? 0?
Zero.
Okay.
So system is like, from here we can analyze like, due to a initial condition, system is a very sensitive. As tiny change, system changes state from one state to another and move forward. Similarly, in the next slides, as
That's
well,
also phase for phase. Corresponding phase for phase.
fixing, converting to the fixed points. This one, and this is a periodic oscillation. This is showing the periodic oscillations.
Okay.
So another example I selected, it is a range from 27.89. If you go here, it is in between here. It is a, here you see the multi-stable states. So come here. So you see, I selected the consecutive time series due to in a PDF, it's not visible. It is a 42, 43, 44, 45, 46. All are sequential with the step size is 0.0012. It changes step size
In initial condition.
in initial conditions. Here it is about this kind of oscillations, and when we move, change the slightly initial condition.
For different parameters, control or what do you change?
Here initial conditions we vary
Only initial condition.
only initial condition. Rest of the thing are fixed.
Temperature is the same and the other parameters are all the same.
I have a question. In the next slide, is possible you try to plot in the same scale, the edges, the axis,
They are
but they put the transitory.
the time.
Maybe
You
you
have-
have to remove the transitory, only put the steady state.
Steady state portion.
Yes, for try to.
It's easier to see, sorry, if I interrupt you. It's easier to observe the formation because the transition effects person do not pay much attention, but you see how it's the same scale, it's the same, and you can even when you can make a plot, if you cut this down, it will be difficult to see probably the stationary state, or even it's displaced from zero with center. In the plot, it will appear will be seen as
Look,
Yes.
for example, the space
Yes.
phase.
yes,
The space phase, maybe you plot different scale, but in the plot 3B, here, this is fixed point.
Yeah, fix it.
In the another,
This one.
no, in the left. What?
This is
But if you see, I can distinguish what is because you plot in different scale.
In which kind of scaling are you referring?
For example, in width scale, you put here which number, in which number. Try to plot if we, the idea if we compare, if we try to compare the different behavior, are the same.
No, but it will that like to plot this one, their position is also changed, so that is why there is
No. But they say that you have to must plot your face portrait in same axis.
same.
When you plot your portrait in same axis, then you see the difference between your face.
In the same frame, not in the same axis, because you know not the proper. But let me see.
The values should be the same of the axis.
This one,
Yeah.
and this one is the same.
Values.
This is the same numbers. I can't see because it's the resolution.
No, it's variate, it's a different.
It's very, yeah, okay. This is the proposal to make it.
The idea is for, it's easy for comparison.
It should be done with the check. It has to be there.
For example, the plot 3A portrait face. This is flat.
You mean same scale?
Yes, exactly. But the idea is if you plot in the same scale, we can compare difference.
It's a good suggestion.
For example, this is a 3A. Good result. And 3A, which is the difference 3A and 3C. Periodics. How you can distinguish this one for 3A and 3C?
The final part will be topologically similar. It will be like limit cycle.
What happened using this solution? You try to plot fast Fourier transform. For example, I suppose I have the hypothesis, or I suppose the plot 3A maybe can be a torus. Because when you have torus, you have double frequency. You try to plot in a portrait face, you try to see like to a donut.
In 3D, in tres dimensiones.
Bueno, you can in this
Con el tiempo,
no, in a specific, but if you get the fast Fourier transform of the time series, maybe I suppose I have 70 or 80% sure that the picture 3A is a torus. 2D torus. Yes. How you measure that it is torus? When you apply fast Fourier transform, you can find two incommensurable frequencies. Or you find two frequencies. If you apply divide one frequency, divide by another frequency, you get an irrational number. This is possible. You have a torus. This is the result because in the bifurcation you have several points. I think it is the like two torus.
it looks like 3A, like a torus, but projection of the torus, it's the projection of the torus because it's traveling the
But following this kind of pattern, when we are seeing
It's periodic.
periodic.
Another is very
time.
a little grueso. How do you say grueso? Thick. A little thick. Maybe it's possible. You use, for example, in this plot, you use time series as portrait face. Maybe we can get additional information or try to apply fast Fourier transform. when you have, for example, if you plot fast Fourier transform, you get a new properties of the behavior of the time set.
I agree with you.
Even if you apply Poincaré section into a method, but you have a more big view or a more big information that you can distinguish the different attractor. In this case, you use different initial condition, no?
Reason, certainly. But that's why we call it like a global exploration of the system. To make indication not so explanation and not details, but to provoke the questions like you did. What is interesting? What is this? Okay.
Why? Because when we see the bifurcation diagram, we can identify very characteristic dynamic behavior. How we prove there are some platforms that can show this behavior, this property. Another platform gives another properties of the behavior, the dynamic. Maybe in the future, some topology measure we can analyze, but in resume good results.
Not only it's a little more because there are some interesting things also. Yeah.
So previously we studied the global bifurcations and illustrated with the time series and critical depth. Now the thing is which you are interested is we are now varying the traveling frequency in nearest natural frequency. This is the natural resonance. So around this one, this is a natural, and we selected less 180 and unbound less. Also, as in the bifurcation diagram, we say decrease the interval also. Reduce the height. It is
because it's the most interesting part. So
because initially it is showing only two states at that oscillations.
The audience is asking, who is giving the conference?
Me?
It is a seminary.
It's a seminar. So it's round table.
Everybody
Participates. It's round table.
go ahead.
These are, first one is for omega 180, omega 192, and omega is equal to 200. All these three pictures preserve the same structures. Bifurcation diagram.
Only local max, yes.
Only like on local mean. We just give you the example of local mean to just discuss that thing. So they originally have a same structure, have some tiny differences as you have been seeing in the scale. This one have some here, now some tiny differences which we observe. So for this tiny reasons, we can conclude in my conclusions what's happening and what we can conclude from this. So going next. So now we are focusing on the homogeneous and inhomogeneous systems. What is effect of external driving force on the system?
In homogeneous, homogeneous refers that we don't have external external. Okay.
Physically, you can avoid this if you have current, but you have no magnetic field.
Well,
there is no force.
in this case, if
you have heating, but periodic heating, but not external force.
In case of there are an external force, what happens with the frequency terms in the equation? Back at
the beginning of the equation.
What happened in the equation? What is the what happened If you don't have external,
Please, because it's vector. See. Okay, this one. Two.
in this case, the omega is 0.
No. Omega is not zero. There is a parametric excitation through the Mathieu effect, but it's only for the heating. You have heating, but you have no force because you have a current, alternating current, but you switch out the magnetic field. No Lorentz force, no force. F1 is zero.
Okay. Well, in this case, it's not necessarily right in different symbol, omega 1 or omega 2, to distinguish that.
For the effect, we started from this effect. The current, alternating current, because we start it's not the independent parameters. Those are not independent from the physical system. Mathematically, we can do it. But physically, it can't be done because the frequency of the electric current, it's the frequency of the driving force, but it's double frequency. It's for the variation of heating, because the current heats equally in this direction and in this direction.
My question is, in case the homogeneous case, for example, no, when less frequency or less and greater frequency, the omega in the external force is different this omega.
There is no external force. It's F1 is equal 0. And if
No, in the inhomogeneous case.
Okay.
In homogeneous case, when you analyze the external force has less frequency than natural frequency, what does mean? Omega, cosine omega is different than this.
This omega?
Yes. Cuando trabajamos para frecuencias menores que la frecuencia natural, ¿sí? Ahí el omega de coseno es diferente al coseno con la fase, o es la misma
no,
frecuencia.
es la misma porque nosotros lo manejamos. Matemáticamente, tengo ecuación, ¿no? Voy a jugar, pongo omega 1, omega 2 y voy a hacer los juegos. Matemáticamente puede tener.
¿Cómo calculas la frecuencia natural ahí? Por ejemplo, sin la fuerza externa.
Kn al cuadrado multiplicado por esto lo que está en paréntesis. Si t esta. Entonces, para explicar todo, cuál son parámetros del físico del material, etcétera, la corriente. Entonces, no es tan rápido. Es esta. Pero lo que vemos, por ejemplo, delta T crece, este término puede ser negativo. ¿Sí? Entonces, a partir de este, si lo calculamos, la temperatura crítica, etcétera. Lo interesante de este sistema es limitante en cierto sentido, lo que tanto omega de driving force y parámetro de excitación paramétrica, parametric excitation, modulation of frequency, son los mismos. Uno va igual que otro. Next, please. Porque tenemos algo interesante.
Yes, the class with the time. Yes.
Okay. So what is emergence?
So these are inhomogeneous and homogeneous systems. And in this part, as you are seeing, both the inhomogeneous and homogeneous system have a same bifurcation diagram, and both reveal the same structure. So come to the frequency response, what's happening? So we selected like temperature, string temperature is a 5 and 34, and we want to explode. So this is the first column is representing the inhomogeneous for 5 and 34.
Is time series or what does?
This is a frequency response and frequency and amplitude. We are observing the frequency response curve.
First you transformó la componente por
Remind me, please. Okay. The first line, it's a frequency response of the system. What do you mean? You change the frequency of here.
29 to 35. We
Uh,
selected a range. It is in hertz. If we convert them, it is from 180 radian per second to 210 radian per second.
frequency response the YX what does
Amplitude,
amplitude of what?
initial amplitude, after.
Amplitude de qué?
no. It's amplitude. Okay. It's
En español si quieres.
en español.
Está.
¿Qué significa frequency response? You change, you give, it's not español. La frecuencia of driving force,
Ya.
you fix it, you have the final amplitude. You change it, you fix the other.
Amplitud de la solución de la ecuación diferencial.
Yes.
Ok, entonces, esto es
The amplitude of the final oscillations. Final oscillations of the
why you in this case change the control parameter is the
No.
phase or the frequency.
So, all the parameters of the system are fixed, but the only what is changed is omega of the driving force, and so it's also how it's related the modulation frequency of
No, the amplitude of the external force.
no. Only frequency. Amplitude is not changed. All the parameters are fixed except we change gradually, not gradually, in time. We fix one, other, a series of frequencies omega.
Well, the control parameter now is
We
the omega.
measure the amplitude of final oscillations. It's in resonance. Como en el efecto de resonancia, que tú haces la curva de resonancia, tú cambias las frecuencias de la fuerza externa y ves que oscilaciones estacionarias del sistema, primero, son muy pequeñas, después empiezan a crecer, llegan al máximo a la frecuencia de resonancia y después decaen. ¿Qué observamos aquí? Aquí observamos que lo vemos poquito, hay un poquito chiquito que corresponde a el efecto de resonancia de la fuerza externa, pero después la amplitud crece y después abruptamente va a la muerte, digamos. Esa es una cosa. Hasan no presentó lo más interesante porque para 5 grados it's not very impressive. Why did the other one which less? I don't remember what this was the temperature.
With the 0. The other one is for 27.
27 degrees. It was quite interesting because here it's for the bad presentation of the projector and so on and so on. There is no scaling of the system also because it's PDF. You can see, for example, what does it mean? Please show me. Which one?
A lo mejor te paras, Eugenio, y no haces con tus...
Which one? Okay, here.
Push button for last.
Which one? Oh. Okay. Okay. And this was very much interesting because you have it's increasing the amplitude with the change of frequencies.
Increase the amplitude time series.
Time series.
Yeah.
Yes, the amplitude of time series. But suddenly it goes to zero. Then it goes once up and then it goes once to zero.
Repentinamente va a esa amplitud a cero.
Yes, with changing, little changing of the driving frequency of the driving force and modulation. It's very interesting effect because it was not mentioned with Luis Javier. It was smooth curve here because I think he don't use the tiny step here. And we missed this because of this. I think
Very last
very much yes, steps. And here it was discovered, and also it was done for the same temperature with Luis Javier. And we missed this. Thank you very much for the presentation.
Hugo dice, ¿para quién pide la constancia de Oris? Who is the...
Back to the monitor over there.
And here you will see that it's
Everybody,
it's okay. This one. What is? I don't remember.
Is it 34? 30. This is the inhomogeneous. And that one is a homogeneous.
Okay. It's homogeneous, inhomogeneous, or vice versa.
No, inhomogeneous.
Inhomogeneous and homogeneous. Okay. We will see the frequency response, homogeneous and homogeneous, it's slightly different. It's more impressive in other temperature. We did this because to compare it with the result of the with Luis Javier. And we found this kind of effect. It's quite interesting because if you have some variation of the frequency, it will be given physically registered. And for 34, we have quite irregular, completely irregular response.
Okay, so what do you expect if you try to repeat this process but using local max?
Come back. Please.
Yes, back. Yes, but if you try to do again, but now control parameter is frequency. Yes, el omega. Now, if you will the bifurcation diagram, but now you fix the delta T zero. Yes, fix this one, but now change the natural frequency. What happened with the bifurcation diagram?
So could be done. We have no answer yet because it could be done. It's other parameter for the bifurcation, other types of bifurcation diagrams, and we will see that it's locally. It's very much interesting because we fix delta T and we only change, but we can the frequency.
Okay. ¿Qué dice la audiencia? ¿Quiere preguntar la audiencia?
Conclusions.
Yes.
Okay. So come to the conclusions, like the driven Mathieu-Duffing oscillator with a wide range give a prominent feature of periodic and multistable dynamics. And as I illustrated through the time series and phase poetry system show high sensitivity by the variation of initial amplitude and the string temperatures. System maintain their global features in the nearest range of the driving force frequencies. And the bifurcation structures for the homogeneous and inhomogeneous look identical. What is the reasoning behind that? They both look identical. Their preliminary structures they preserve through the interplay between the Mathieu type parametric excitations and Duffing type nonlinear stabilization. And the external driving force is a secondary as compared to the nonlinear effects. So, what is our future work? We will explore furthermore a detailed analysis of Mathieu-Duffing driven oscillators, focusing on the driving force amplitude, temperature variation, initial displacement amplitude. And also, we will try to introduce nonlinear coupling between different variation modes, and we will see how our structure of dynamics will appear. So these are our recent achievements. We will publish our chapters in which we detailedly explain our mathematical exploration of our mathematical model of
The basic system of equations.
the coupling driven Mathieu-Duffing oscillators. These are the references. Anyone can see.
Bueno, gracias. Hasan, now we will start the question section. Please, any question? Or maybe during the all process of the talk, there were many questions. Any question? Hugo,
We have more questions.
are there any question in the audience, in the online? Ya se fue.
No question.
No, nada.
Bueno, pues, no question?
No questions.
No question. Well,
We will do it when you close.
Yeah.
The session.
thanks for presentation, Hasan. I hope at the end semester, we will give Hasan constant that you participate in this conference.
But there is I present in the previous one and I.
Well,
At the end of the semester.
I don't get my.
No, you can download of this. Remember in the Lyapunov, summer Lyapunov,
Okay.
Hugo sent a link.
Okay.
In this link, you can download the several constants of you participate in different conferences.
Muy bien.
Just try to find this one.
Okay.
Well, thank you, Hugo. Thank you very much. Well.
Can we